Okay, in this last video of the semester, we're going to talk about B trees and maybe just a touch about graphs. Okay, so in a normal semester, we sometimes get to graphs, we sometimes don't. So no big deal there. We do usually get to B trees to some degree. So I think it's important as you move forward that you read through the section on B trees and the chapter on graphs, just so you're prepared as you move into your classes, those classes will assume that you covered this, okay? So let's talk about the idea of a B tree. So we've discussed binary trees. We've talked how they can be useful in storing information. But as the information becomes more voluminous, there's much more data to get through, okay? Then a binary tree is going to take too many jumps to get to the end. Okay, so even with its efficient searching of knowing where to go every time, we're still going to have the problem of it's a long way down. There's a whole lot of levels. Okay, we mentioned a little bit in the last video about 2-3 trees, which allow there to be either 2 or 3 links basically from each node. Okay. So the idea of a B tree then is going to be even more a development along those lines. Okay, so a B tree is in essence a way to do some indexing. Okay, that looks too big. Yeah, indexing. Okay, so in the olden days when we had encyclopedias, I'm not sure you've ever seen such a thing or used them, but basically they tried to put all of the world's knowledge into some volumes of books. Okay, so it was not one gigantic book that was ordered. Okay, where you could do a binary search by looking in the middle and in the middle and the middle. That would have taken forever. Okay, instead it was divided into volumes. There was an A, a B, a C, and so forth. Okay, so that's kind of the idea behind the B trees. Okay, so the B tree is a more generic way of looking at something called an M-way search tree. Okay, so we have this M-way, it's a way search tree. Okay, and these trees, each node has at most M children. Okay, so it has the following characteristics. Okay, so each node is going to look like, okay, so there's going to be a series of values, and then between them, and depending on how big M is, I'll just pick some random number here. Okay, so you have values here. Okay, so you have an A, a B, a C, a D, an E, an F, a G, and an H. Okay, so all of these would be values of some sort. And the links here, this is going to be things that are less than A. Okay, this link is going to be between A and B. Okay, this is between B and C, and so forth until this is greater than H. Okay, so that's the general way these look. Okay, so all of the keys, which any of the pointers point to, okay, are going to be less than the key itself. Okay, so it has that property. Okay, and the subtrees then are also themselves M-way search trees. Okay, so to look at an example of one of these, okay, so if we have, and the book draws it this way, we have 80 as a root node, it can have up to, this is a 5-way tree, so it can have up to 5 child nodes. Doesn't have to. Okay, in this case it's going to have just 2, so I'm going to put 1 there and 1 there. Okay, so this one goes off that way, this one goes off that way, so everything to the left is less than 80, everything to the right is greater than. Okay, so this is going to go down to a more complex guy here, it's got a 40 and has a 50. Okay, so that means there's going to be a link there, a link there, and a link there. Okay, so from this link less than 40, this link between 40 and 50, and we'll have to decide which way which way does 40 go, which way does 50 go. Okay, and then this way are going to be things that are greater than 50. Okay, and over here we're going to go to a 90 and a 125. And again, we have things that are less than 90, between 90 and 125, and greater than 125. Okay. So in this case over here, we could have an 8 and a 16. Here we could have 45 and a 48. Over here we could have an 81 and an 85. Those are both less than 90. Okay. Less than 90, but greater than 80. Okay. Here we could have a 92 and a 95, because those are between 90 and 125. Over here, we could have a 130 and a 155. Okay. So note again, it has the basic binary search tree idea that everything left of here is smaller, everything left of there is smaller. So, okay. These M trees tend to be at the same, we want to keep them at the same level. Okay. And as we're adding, we can have up to 5 children, okay, which means up to 4 things can be there. Okay. So as we add information to this tree, okay, we can push more things into our indexes to hold more at these levels. Okay. So this gets us to the idea of a B tree of order M. Okay. So it has a couple of additional properties. The first one, okay, so it's an M-way search tree. Okay, it can be empty or it can have the following property. Okay. All leaves are on the same level. Okay, so like this one, all the leaf nodes are down here. So we're gonna enforce that for a B tree. Okay. Second part is that all internal nodes except the root have at most M, so not empty, children, and at least that's a ceiling function, okay, M divided by 2 children. Okay. And then 3, the root node has at least 2 children if it is not a leaf, and at most M children. Okay. So what we're doing with this definition then basically is that we're making sure that our tree is going to be somewhat balanced, right? That we're going to not have all of the data into one spot. Okay. So there are examples in the book of some coding that we can do there. Okay. What the insertion does, go through a quick example of the insertions. Okay. So if we want to insert a 40, 30, 70, and 5. Okay. So all of those can fit, and they would be in order. with a 5, 30, 40, 70. That can all be at one node. Okay, so no issue there. Now we're going to insert a 16. Okay, it can't fit inside of here. We already have the maximum 4. It's the 5-way tree. Okay, so we're going to have to split things up. So we're going to go roughly to the middle to split this one. We're going to go roughly to the middle. Okay, and we can just at random, in this case, we're going to pick the lower of the two middle values, which is 30. Okay, so we're going to move 30 is our new root. Pull that up. Okay, it's going to have 2. Okay, we can then on this side put the 5 and the 16. So there's a link there, a link there, and a link there. Okay. And on the other side, we can put the 40 and the 70. So again, link there, it's empty, link there, link there. Okay. So when we were at this point, we're okay because all the leaf node, which is just the one node, are at the same level. Okay. And now that we moved down to here, we're also okay, and that all the leaf nodes are at the same level. Okay. So now let's say we want to insert more. We'll insert an 82 and a 95. Okay. So the 82 and the 95, we have room for them both in that node. Okay, because we have up to 4. That's where they would go. Again, 82 greater than 30. It's going to go here. There's room for it, so we're good. Okay, so I can just go ahead and increase this one. Put the 82 here first. So one more link over there. The 95 will go in the same way. They have to be in the same order. So now we're good there. So now we're fine. We don't have any issues there. Okay. So we're a little unbalanced, but everyone has at least the m divided by 2 ceiling of that. So everything has at least enough data. Okay. So if now we want to insert a 100 into this list. Okay. At the 100, that's a 95, doesn't look like it. The 100 we need to go into this box, okay, but that box is full. So what are we going to do? We have room in the root node to expand, okay? So which one are we going to expand? We're going to, again, go in here and pick one of the middle values, okay? And we'll figure out, we can do that through the algorithms, how we're going to do that. So in this case, we're going to add 30 is already there. We're going to bring the 82 up to the root level. Okay. Reorient things that way. So now we have that. So this doesn't change. We still have the 5 and the 16 over here. Okay. But now we have a node here that's the things that are between 30 and 82, which are going to be the 40 and the 70. Okay, and the things that are greater than 82, which are going to be the 95 that we had before and the new 100 that we're at. Okay, so that's how we would continue to add on to those things. Okay. Again, the way a search would work, if we're searching for the 100, we go here and we say, is 100 equal to 30? It's not. Is it less than 30? No. So we don't take that one. That one's out. Is it between 30 and 80? No, it's not. Is it equal to 82? No. It's greater than 82? Yes. So we're going to follow this way. So we'll start here. Okay. Is it 95? It is not. Is it less than 95? No. Is it 100? It is. So we find it in that one. Okay. So it's a pretty efficient way to do things. Okay. So, and that's kind of the basic rule that we're going to keep inserting, adding things into our basic structure. And when we need to, we'll pull up more data, okay, until we fill everything up, fill everything up, okay? So for a given level, there'll be a maximum number of things that you can have, okay? So to max out this 2-level tree, you could have at most 4 in the root. Okay. Each of those 4 children could also have 4 children. So that's how you can figure out the maximum number as far as that goes. Okay. So that's the generic idea. So again, on the exam, there could be a question that asks you to insert one, again, just on paper. We're not talking about doing any coding. The coding is there in the book. It's worthwhile trying to figure it out. As you can imagine, deleting sometimes is a little bit dicey. If you delete something that's a root node, you have to promote something else up. Okay, so there can be a lot of things to do there. Okay, so again, that's fair game. No homework, programming homework on this. Okay, so you don't have to worry about that. Okay, just know what's going on. Okay, so the last thing, again, just to give you a little bit of an overview, it's things that you should know, you should have hit already in math class, but if not, we're going to go and talk about it. That's the idea of a graph. Okay, so a graph is going to be, so a graph G is going to be this ordered pair V and E, where V is a set of vertices and E is a set of edges. Okay, so we could have something like our vertices are 1, 2, 3, 4. So in this case, V is equal to set 1, 2, 3, and 4. Okay, and if our edges look like this, our E would look like, these are then ordered pairs. Okay, so 1, 3 is a pair. Okay, and you could figure out this needs to be again ordered pairs. You can figure out how to do this here. So let's do a 1, 3. I could just say the 1, 3 alone look like a 13. Okay, so that is one edge. 1, 4 is an edge. Okay, and 2, 4 is an edge. Okay, so that's going to be the basic idea of the way we would look at a graph. Okay, so some variants of the graphs you can have. What I've drawn is an undirected graph, which means that the 1, 3 refers to from 1 to 3 and from 3 to 1. Okay. We can make those a directed graph, in which case they're only in one direction. Okay, so we could have that, we could have that, and maybe this does that, but it also goes back that way. Okay, so in that case, we have to be very specific about our edges. So our edges are still 1, 3. Okay, we know it's a directed graph. By definition, we would define it as a directed graph. So we know that doesn't mean 3, 1. Okay, we still have 1, 4. But now we have 2, 4 and 4, 2. Okay, so those are the 2 different sets of edges that we have. Okay, so the other kind of graph that we can have, okay, so this is a directed, you can have a weighted graph. Okay, so a weighted graph is going to have some value or cost associated with each of the edges. Okay, okay. So when we're looking at how we're going to represent graphs, okay, so there's no good way to code these directly. Okay, so one option is through an adjacency matrix. And the adjacency matrix is going to basically create a matrix. Okay, so if we have a let's see, 1, 2, if we have 5. Okay, so let's do a picture here. 12, 4. So give it a break. So we're going to represent a 1, that goes to a 2. Okay. A 3 that goes to the 1. The 3 goes to the 4. The 1 goes to the 4. And there's a 5 that both the 2 and the 4 go to. Okay. So we're going to create, we have 5 vertices. So we're going to have 1, 2, 3, 4, 5 down, and 1, 2, 3, 4, 5 columns. Okay. And at each point, we're going to put in a 0 if no edge, and a 1 if there is an edge. Okay. So we can label these, although they don't go on the matrices. We'll put them in here for now. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay. So from 1, we're going to look at the row from 1. From 1, we can't get to 1, so there's a 0 there. We can get to 2, there's a 1 there. We can't get to 3. We can get to 4, and we can't get to 5. Okay. From 2, 2 can only get to 5. Okay, so 2 has a 1 there, and a 0 everywhere else. Okay. 3 can get to 1. It can't get to 2. It can't get to itself. It can get to 4, cannot get to 5. Okay. 4 can only get to 5. And 5 cannot get anywhere. So this adjacency matrix, and again, you would typically not put those in there, is equal to this graph. Okay. So, and that's the way we typically are going to do it. Okay. The other way we could do it, okay, and this is for a different graph. Let's get the graph that this one's for. So the other way is to an adjacency list. So this time we're going to look at 0 can go to a 1. And note these are directed graphs, which can go to a 2. The 2 can go back to the 1. There's a 3, get to from there. There's a 4, which can go to there. We go from 1 to 4, and we can go from 2 to 4. Okay. So we're going to do an adjacency list this time, and it's going to be for each of our vertices. Okay. So for 0, our link list, okay, we can get to a 1. Okay. And we can get to a 3. Okay. Note this does not mean you can get from 0 to 1 to 3. 0 goes to 1 and it goes to 3. Okay. 1 can go to 2 and 4. Okay. 2 goes to 1 and 4. Okay. 3 doesn't go anywhere. And 4 only goes to 3. Okay. And you don't see this as often, but you certainly could. So something you can do with that. Okay. So once you have your graph, there are some operations that we can define. And these are in the book. I'm not going to show how they get done. Okay. But we can start off with, you have to be able to create the graph. Okay. So you have to use either the matrix, which we typically do, or do the list. Okay. So you got to be able to allow the user to input in some way through a file or through, from an array, whatever. Okay. You have to be able to clear the graph. You have to have it is empty. See if it's empty. Okay. You have to traverse the graph. So with the graph, you get the idea of paths. If I start at 4, I can take a path only to 3. But from 0, I can go from 0 to 1 to 2 to 4 to 3. Okay, so in that case, if you ask the question, can I go all the way around? Well, I can go there, and then there, and then there, and then there. So yeah, I can go all the way around. I can't go all the way around and get back to the same place I started though. Okay, so that's all on the traversing the graphs. Okay. And then finally, sometimes we're going to want to print out the graph. Okay. So the book defines an abstract data type for this, and then it goes through and it shows how we can create this and then go through the traversals. Okay. So the traversals with a graph we typically talk about, and these are going to come in later with other places, so it's worth mentioning here. We have the depth first. So with the depth first, you're trying to get away from root, get away from the start, I guess. Don't skip letters. Okay, so if you had whatever your data structure did, whatever you've got, okay. With a depth first, if we start here, we're going to go here and then go someplace else. We're going to keep moving away and then only then go back and see what we missed. Okay, that's a depth first. The other option is a breadth first. Write that so you can read it. With the breadth first, before we go to one level, we're going to go to all the ways we can get to from there. Okay? We then only then do we go to the next level. So we're staying close to home as much as we can, exploring all of the options. And those are the basic ways we're going to be going through those. And depending on the problems that you're trying to solve, that's how it's going to be. Okay? And then again, more terminology you're going to need moving forward. In a weighted graph, that's just a graph where there's some cost associated within each link. So each edge. Okay, so if that's the case, we can get to ideas such as the shortest path. Okay, or the smallest weight to get to all the vertices. Okay, and that would assume that you have a connected graph you can actually get there. Okay, so the shortest path turns out to be a pretty important factor to go forward, especially in networking. We talk about representing the network as a graph, okay, and then we're going to worry about the weights that become the current time it takes to take that particular connection, that wire or means between two ends. Okay, so the last concept we're going to talk about here is the idea of a minimum spanning tree. It's a term that you will see again, obviously in algorithms for sure. Okay, so we'll do the following graph. It takes us a little bit to get here, but to get the idea here. Okay, so the minimum spanning tree is going to be a subgraph. Okay, that's going to include a way to get to all of the vertices, and it's going to do so in the most efficient or least cost way. Okay, the smallest number for the total. So we've got This is an undirected graph. Do it either way. Got 1.6, 2 to 3, 5 to 2. Okay. So this has a cost of 6. This has a cost of 5. There's one there with a cost of 2, cost of 7, cost of 5, there's a cost of 4, cost of 8, cost of 2, cost of 10. Okay. And there are different algorithms that you could cover here to figure out how we're going to do this the smallest way to get there. Okay. So the book does or does not talk about them. Let's see if it does. Yeah, not so much. Okay. But basically, a minimum spanning tree, you have to connect everything. So for 0, our cheapest path here is this one. So we would do that one. I would keep adding in the cheapest ways. Okay, so this one becomes the next cheapest, the 5. Okay. The next cheapest is that one. As long as it goes to something I haven't done yet. Then the next cheapest is this one. That's the 4, and then the 2. Okay. Oh, we have to get to that one somehow. So that one, cheapest way. It's a weird graph that crosses. Would be there. Okay. So that would be the in red is the subgraph. Okay. So again, you would delete the nodes here that you're not covering. Okay, to get your minimum spanning tree. Okay. So again, I'm not going to test you at all on graphs. It's just some information that you should know. And I encourage you to look through the book to be ready for algorithms class, which is the next one that you typically take. Okay, so that's it. So I put out there in an email or a message on Moodle that if anybody wants to have a review, then that's perfectly okay to do that. We'll have to try to time. I had a review last time and nobody came, so, which is fine. I mean, it doesn't matter to me. But if you want to have a review, that's okay. I'm sorry, it's dark in here. I've moved offices, by the way. I'm up on the 2nd floor now in Darden. If you happen to be on campus, I won't be here until the semester much. But anyway, so yeah, just read through the messages. So I'm recording this on Monday. So problem set 5, I think, is due tonight at midnight. Okay, I'll put out a new problem set 6. The last problem set will go out in the morning. Okay, as well as I'll grade and put some kind of solution guide to problem set 5. Okay, and then the problem set 6 will be due Thursday, so you only have a couple of days to do it. So I'll try to keep it brief. Okay, Thursday will be the day. If people want to do a review, we can. If not, then the exam will be on Friday. And I posted a time. I think I said 11 to 1 or 10 to 2, 10 to noon or something. I don't know. Anyway, I posted an email. No one's responded. So please go into your messages and respond with if that time's okay. Yeah, I think 10 to noon is what I'd suggested. If that doesn't work for people, let me know. Okay, you have to be on Zoom. The exam will be, this time, will be partially programs like before, but there will be some essay type questions, which are about a half-page answer. Okay, so you may maybe asked to explain topics. A good question would be things like, what's the difference between, or when would you use a stack versus a queue? And, you know, maybe some questions about different sorting algorithms and their efficiencies and all that stuff. Okay, so if I make my head bigger, I'm not quite as dark. Okay. Anyway, so if you have questions about any of that, make sure that you let me know. Again, the test open book, open note, but not open internet. So don't be Googling for answers because I'll be able to tell almost always. Okay. So if you have questions, make sure you let me know. Now's the time. It's all coming together this week. So make sure that you let me know as soon as you can. And we can Zoom, we can text back and forth, whatever you need to do.